Welcome to VSEPR, Part 4. Derivative shapes. Which are also referred to as the molecular shape. And we're going to talk about the impact of lone pairs. Hopefully now you're really comfortable with those 5 basic shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. But we haven't talked about why, if it makes a difference. We said an electron group is defined as a bond. It didn't matter, right? Single, a double, or triple bond, or a lone pair. But what is the impact of having a lone pair on the shape? So our first electron geometry that we learned about was linear, which has the general formula AX2, where X is a bonding group or a lone pair. And for linear, we have a central atom and then 2 groups attached to that central atom. And we have 180 degrees. If I replace one of these bonding groups with a lone pair, it doesn't really change the geometry here. So we don't really talk too much about this situation where I have just a lone pair of electrons on the central atom here. It's still going to be linear. But it does start to matter if I start to look at something like trigonal planar. So let's look at trigonal planar. So trigonal planar, it's the general formula AX3. And we have a central atom with 3 groups attached to it at 120 degree angles. So I like to look at this kind of thing in terms of examples. An example of something like this is formaldehyde, which has a Lewis structure. And remember, we're only talking about the lone pairs on the central atom. So here, this is carbon, and it's got 3 bonding groups, no lone pairs. So bonding group and lone pair, sorry, get ahead of myself sometimes. 3 bonding groups, or BG, and no lone pairs. And so when I have 3 and no lone pairs, the actual molecular shape made by the atoms itself is going to be the same as the electronic geometry, and you're still going to get trigonal planar. So if I was to sketch out what formaldehyde looked like, it would look like the drawing that I drew. Like this, with my 120 degree angle. And it's going to be trigonal planar. But what happens if I have a Lewis structure like sulfur dioxide here? It's got a lone pair sitting on that sulfur. And now I only have, make that look a little better, now I only have 2 bonding groups. Remember, we do not count the number of lines. So if I'm going to look at my groups going around that sulfur, I got 1 group here, and one group here. And then in the middle here, I have my lone pair. So that's my 3 electronic groups. And I have one lone pair. And so the best way to look at this, and how I like to look at this, is I can take my mouse here. Let's see if I can create something a little better. So I can almost literally erase this. So I'm going to draw my, in general, my basic electronic geometry here, which is trigonal planar still. That's my basic electronic geometry. But if I want to know what this thing looks like as a molecular shape, under microscope, I can't really see that lone pair. So I can literally erase it there. And what I'm left with, so it doesn't change much, but what I'm left with is what's called, so I'm going to replace that with my lone pair sitting up here. And what I'm left with is a bent geometry. The other thing about this geometry in lone pairs, so we can think about lone pairs, that lone pair belongs entirely to my central atom. Remember, if I was to draw in electrons, the line represents 2 electrons, right? And we just simplify it and we get rid of these dots, but that line represents, in our case, we actually have a double bond, so it actually represents these 4 electrons here. But these electrons are shared between these atoms. But the lone pair belongs solely on that central atom. So he likes to be a little greedy, and he takes up a little bit more space than a bonding group would take. So he takes up a little bit more space, and because of that, he kind of pushes this bond angle, which naturally would be 120, he pushes it a little smaller. So my bond angle is 118 degrees because lone pairs take up more space. And so it squishes my bond angle a little bit. So it goes from 120 down to 118. So let's look how this plays out with other geometries. If we look at 4 electron groups, and again, I like to work with this with example. The most classical example of 4 electron groups is methane. And so this is a Lewis structure for methane, or CH4, and we can see pretty easily that methane has 4 bonding groups, no lone pairs, and this then forms the tetrahedral geometry. And my very simplest tetrahedral, again, that little spaceship model of a tetrahedron, and it's got 109-degree angle. And we'll write it out as tetrahedral, which is the same as the electronic geometry. We'll look at the next Lewis structure we'll look at. Is NH3. Or ammonia. And so this has 3 bonding groups. We can see them. 1, 2, 3, and then 1 lone pair. I like to circle my groups, or at least mentally do this when I'm looking at these to identify the bonding groups. And again, we're going to look at it the same way. I like to go ahead and sketch out the electronic geometry. If you want to see it, little balls here represent those bonds. And I'm going to take away the 1 and replace it with a lone pair. And this is kind of looks like a bit of a squatty pyramid without a top, because that lone pair is sitting up there. And this is called trigonal pyramidal, because it looks like if I connected the bottom it would have a trigonal base point at it. And the angle, very similar to the example in the previous trigonal planar example, is again, this lone pair takes up more space and it pushes these bonds slightly closer together. And it's about 2 degrees for every lone pair. So this is about approximately 107 degrees instead of 109, because that lone pair is greedy on that central atom. And lastly, we'll look at the structure for water. And this is really a classical 3 comparison. So here's water. And water has 2 bonding groups and 2 lone pairs. And really, water is one of the most important compounds that we look at in this class. We talked about it in the What's Important About VSEPR video. Is the shape of water really dictates a lot of the properties that water has. And so I got my 2 bonding groups and my 2 lone pairs. And it's still going to go into that tetrahedral geometry. So again, I'm going to go ahead and draw that. Here's my tetrahedron. And in this case, 2 of my bonds that I show here are going to disappear. That's 1 lone pair. And that's 2 lone pairs. And what am I left with after that? This is called bent. So when I put those lone pairs on, it's still, these guys take up that space. But if I look at just what's made up of my bonding part, it's bent. And because now I have 2 lone pairs, the angle gets pushed even closer together, and it's got a 105 degree angle on water. So this is why water is bent. It is not linear because it is falling into that tetrahedral geometry. And when I go into the tetrahedral geometry, those 2 lone pairs, they take up space on that central atom and they are pushing that bond closer together. And so I end up with that 105 degree angle for water. Moving along with this, we're going to look at 5 electron groups. I'm going to speed this up a little bit so you get the idea. So for 5 electron groups, again, I'll start with an example. We'll look at phosphorus pentachloride. And it's a really good idea to practice these and prove these Lewis structures to yourself. And again, just in the interest of time, remember that these lone pairs are sitting out on the chlorine. I'm just not drawing them to save a little bit of time. But they don't impact the geometry around that central atom. So just be careful because it can be tempting to count all these little lone pairs as well. We have bonding groups. We have 5 bonding groups here. 0 lone pairs on the central atom. And we're going to have that trigonal bipyramidal, which I like to draw kind of coming up line, and then my triangle going around the middle. And so this is trigonal bipyramidal. This next geometry is one of my favorite. I'm going to draw SF4. And these lone pairs sit here on the fluorine, and there's one lone pair in the middle on this sulfur atom. You can see him there. That's my lone pair. And I have 4 bonding groups, 1 lone pair. Now what's interesting about the trigonal bipyramidal geometry, I'll go ahead and resketch it. Right. So I have 2 different types of bonds, because remember the angle here is 90 degrees and the angle going around the middle is 120 degrees. And given this idea that lone pairs want to take up as much space as possible, the place that they're going to pick is not going to be 90 degrees from 3 other bonds. They're going to go around the middle because they have 120 degrees around the middle. So the lone pair is going to go on the equatorial because it has more space. And this is one of my favorite geometries, because if we turn this little guy on its side, and put the lone pair up top. So I just turned them over on the side. This looks like the seesaw. So you can visualize this as like a little seesaw with a couple little kids sitting on it. And that's where it gets its name, seesaw geometry. We continue this pattern. Look at this guy. This is bromine trifluoride. And bromine trifluoride has 3 bonding groups, the 3 fluorines, and then 2 lone pairs. And similar to the above, the lone pair, so again, I'm just drawing the basic geometry for the trigonal bipyramidal, and the lone pairs are both going to go on that central atom on the equatorial, again, because it has more space there. So you end up, and this shape is called, again, if you kind of turn this thing on its side, the bond angle gets compressed a little bit here. It's not as dramatic as the tetrahedral, but it gets its name because it is compressed a little bit. If I turn this on its side, they call this distorted T. It's distorted because this bond angle is slightly compressed around 89 degrees because the 2 lone pairs sitting around the middle. And lastly, if I take away, or if I add one more lone pair to this guy, we can look at this ICl2 ion. And this is an ion with a -1 charge. But that doesn't, again, it doesn't impact. Don't let that intimidate you. It doesn't impact what this geometry is going to look like. I have 2 bonding groups here, right? The 2 bonding groups and 3 lone pairs now. 1, 2, 3. So 2 and then 3. And I really do like to always sketch out that general electronic geometry because it always reminds me where things come from. And I'm going to also, again, with my 3rd lone pair, I'm going to take up another axial portion. So 1 lone pair, sorry, equatorial. 2 lone pairs, always going along that central triangle in the middle. 3 lone pairs. And if we look at this, what do we have left? We have a line with 180 degrees. So it actually can come all the way back to linear geometry. But those lone pairs are here and they're taking up space. So it's a little different than the linear geometry for 2 electron groups. So those are the derivative geometries for 5 electron groups. And the last set we'll look at here will be 6 electron groups. And we're only going to do 2 of these because the rest of them will follow this pattern. So we can look at SF6, which is a sulfur with 6 fluorines around it. These expanded geometries are really interesting. You don't see them a lot, and you often see them with fluorine because fluorine is a very electronegative atom, and it can suck electrons away from all kinds of things. So you see a lot of fluorines in these because fluorine loves those electrons. And you see it's often used a lot in etching in electronics industry. You don't really see too much of these molecules outside of the microelectronics industry. So bonding groups, 6, lone pairs, again, central atom, 0. And this is my octahedral geometry. And I like to draw that like this, just really simple. All 90-degree angles here. Octahedron. And then my example here with 1 lone pair is bromine pentafluoride. I've got bromine again. I could show all these lone pairs, and it's good habit to do that, but just in the interest of time, I'm going to just not show them, but just remember that they are there. This is 5 bonding groups, 1 lone pair. And same with the previous geometries, I'm going to go ahead and draw my octahedron. Now remember that all of my angles in the octahedral geometry are 90 degrees. And so it does not matter, unlike the previous example where it mattered if I went in the axial or the equatorial. These are all 90 degrees. This is a symmetric molecule, and so it doesn't really matter what I pick. So just out of, I'm going to pick this bottom guy. And we'll put that down there. And what you're left with when I take out the bottom is a square base pyramid. Square pyramidal. The last example that I'm going to do It's another ion. ICl4 ion. It doesn't really matter how you draw the Lewis structure either. And this has got a -1 charge. This, I have the 4, 1, 2, 3, 4, 2 lone pairs. So I got 4 bonding groups, 2 lone pairs. Draw my octahedral geometry. So the first one we picked just out of convenience was the bottom. You did it all for me there. So I'll replace that one with the bottom. And see, when I get a second lone pair, it does matter because, again, that lone pair does want to take up the most space. So it's not going to take up a 90-degree spot from the original lone pair. It's going to go opposite of the first lone pair that you put in. So we'll take the opposite of the first lone pair. So it's going to go directly across. And that gives it the most space. And you'll notice that what I'm left with, if I connect these points, what do I have? This is a square planar geometry. So that was the molecular shape of this guy. So that concludes all the derivative geometries. I'm going to leave you with this. Practice these guys. It can be tempting to try to memorize this as a chart. It's much better to look at these and look at the geometry and visualize it. Go back and watch the Simple 3D Models at Home video. Visualizing is the best way to do this, and these names are very much these visual structures for these molecules. So I hope this helped. Thank you, and have a good rest of your day.